In question 1, we will be exploring the union find data structure. So just as a quick refresher from lecture, we improved upon our naive implementation by introducing union by size as well as path compression. So weighted quick union is essentially quick union but slightly modified in order to limit the height of the tree structure. We need to keep track of the number of elements and always link the root of the smaller tree to the larger tree. So to achieve this, we use the same parent array as before. Our isConnected method wouldn't change, but the connect method needs to now keep track of sizes. And two common approaches include using negative values in the parent array for root nodes to represent the size, and also just keeping a separate size array. Our second improvement discussed was weighted quick union with path compression. So with path compression optimization, we connect the nodes we traverse to the root whenever we check if two nodes are connected. So for example, if we wanted to check if nodes 15 and 10 are connected, we would need to traverse all of the blue nodes. As a result, all of these nodes will be connected to 0 after the function is called. So our final structure will end up looking like this. In question 1.2, we are asked to draw the union find tree after executing the following sequence of methods without path compression. We break ties by choosing the smaller integer to be the root and begin with all nodes unconnected. Also, calling find on some x will return the root of the tree. So union 2, 3 would connect nodes 2 and 3. Then union 1, 2 would connect 1 to 2, with 2 as the root since it is part of a larger tree. Then union 5 and 7 would connect nodes 5 and 7. Then we union nodes 8 and 4. And unioning 7 and 2 would connect 7 to 2 since 2 is part of a larger tree. Then calling find 3 will return the root, which is 2. Next we have union 0 and 6. Then unioning 6 and 4 will connect 4 to 0. Then union 6 and 3 will connect 0 to 2 once again, since 2 is part of the larger tree. Then find 8 and find 6 will return 2, since 2 is the root. And this will be the returned array. So the element at each index of the array represents its parent. So for example, at index 0, we have the element 2, which means the parent of node 0 is node 2. If an element of the array is negative, then the corresponding node for that index is the root, and the absolute value of the element is the size of the tree. So in our example, we have that the element at index 2 is -9, which means we have node 2 as our root and a union find tree with 9 elements. In the last part of question 1, we want to perform the same sequence of operations again, except this time we're going to use path compression, so all of our union methods would stay the same. When we call find 3, we look along the path between node 2 and node 3. Since node 3 is already connected to node 2, the tree stays the same and 2 is returned since it is the root. Next we do more of the same unions, and finally we call find on 8, which results in traversing the path from 2 to 0 to 4 to 8. So we're going to connect nodes 0, 4, and 8 to 2. And finally we return 2. Similarly, when we call find on 6, we traverse the path from 2 to 0 to 6, which means we're going to connect nodes 0 and 6 to node 2, and return 2 since it is the root. And this will be our array representation of the structure. So once again, since 2 is our root, the array at index 2 is -9, meaning there are 9 elements in our structure. The element at the 7th index is 5, since the parent of node 7 is 5, and the rest of the elements are 2 because everyone else's parent is node 2.